Have you ever looked at a river and just wondered, what's keeping it safe? What's the hidden science that makes it a healthy home for life? Well, today, we're going to pull back the curtain on one of the most critical tools in environmental protection, the fish toxicity test. I mean, it all really comes down to this one big question, right? At what point does a chemical spill or some industrial runoff cross that line, from just being in the water to being flat out deadly? Figuring that out isn't just guesswork, it's a very precise science. And the key to that science? It's fish. You've heard the saying, a canary in a coal mine, right? How canaries would warn miners about toxic gas? Well, for our rivers, lakes, and streams, fish are basically that. Their health gives us a direct, living report card on the health of the entire water system. Okay, so if fish are our aquatic canaries, how exactly do we, listen to them? How do we translate what's happening to them into something useful? That is exactly where fish toxicity testing comes in. It's the standardized, scientific way of turning fish health into cold, hard data. So why go to all this trouble? Well, because these tests are absolutely fundamental. They're what help regulators identify a contaminated river in the first place. They let us predict just how bad a chemical spill might be. And most importantly, they help us set real, legally enforceable safety limits for pollution. It's all about protecting the entire web of life. Now, to make those safety limits actually mean something, scientists can't just say a chemical is bad. They need a number, a clear, repeatable metric for just how toxic something is. They need to find the exact point where it becomes deadly. And that magic number is called the LC50. This is the gold standard in this field. It stands for lethal concentration 50%. Now, it's not the point where all the fish die, it's the precise concentration that's estimated to be lethal to exactly half of the fish in a test group. Finding that tipping point is the entire goal. So, how do they find that exact 50% mark? Well, it's based on a really simple idea called the dose-response relationship. Honestly, it's just common sense. The more of a toxic thing you add, the stronger the negative effect. So scientists test a whole range of doses, from super low to very high, to watch how the fish respond and pinpoint exactly where that 50% line gets crossed. And this brings us to the actual method they use to find that LC50 value. It's known all over the world as the 96-hour acute toxicity test. This whole process is incredibly standardized because the results have to be reliable, no matter where in the world the test is done. It runs for exactly 96 hours. That's 4 days. They use at least 7 fish for every concentration they test, and this is key, there's always a control group of fish in perfectly clean water. And get this, if more than 10% of those control fish die for any reason, the entire experiment is considered invalid and has to be thrown out. They take this stuff very seriously. Over those 4 days, scientists are on a really strict schedule. They're checking on the fish every 24 hours, recording everything. They're not just counting, they're also looking for signs of stress, like if the fish are swimming weirdly. And here's a cool detail. The fish aren't fed during the test. Why? Because you don't want their waste messing with the water chemistry and interfering with the results. But look, getting a reliable LC50 isn't as simple as just putting fish in some water and counting what's left. The real scientific challenge, the true rigor, is in controlling every single little variable that could possibly mess up the results. Let me give you a perfect example. Water hardness. The exact same amount of a toxic metal, like copper, is way more deadly to fish in soft water than it is in hard water. That's because the calcium and magnesium in hard water basically act like bodyguards, shielding the fish's gills from the toxin. It's a fantastic example of why you have to control every last detail. And it's not just hardness. Oh no. Scientists have to keep the temperature rock solid because that changes a fish's metabolism. They have to make sure there's plenty of dissolved oxygen for the fish to breathe. The pH level has to be perfectly stable, since a small shift can actually make a chemical more or less toxic. Even the fish themselves have to be healthy and settled into the lab for at least 10 days before a test can even start. Okay, so you do all this incredibly careful work in a lab and you get this one number, the LC50. So what? How does that number actually get out of the lab and into the real world to protect a river? Well, this is where science directly becomes policy. It's actually pretty simple. A chemical's LC50 value is used to slot it into a specific hazard category. If the LC50 is super low, say less than 1 milligram per liter, it gets classified as highly toxic. And that classification then determines everything, from the skull and crossbones you see on a warning label to how it has to be transported. Sometimes the rules are even more direct. For example, in India, some industries have to test the treated wastewater they release. And the rule is simple. When they run a 96-hour test, at least 90% of the fish have to survive in the pure, undiluted wastewater. It's a straight-up pass-fail test based on this very science.
And that's really the whole point. This quote from the research material just nails it. This isn't science for science's sake. The entire purpose is to generate hard, quantitative data, actual numbers, that regulators can use to set and enforce safety limits to protect our water.
So the next time you're near a clean, healthy river, you can appreciate some of the invisible science that's working behind the scenes to keep it that way. This meticulous 4-day test is a quiet hero of environmental protection. But it does leave you with a big question. If this is what it takes to safeguard our rivers, what kind of science are we going to need to protect our vast, complex oceans?